So we're taking a look at the second half of the Coulomb's Law practice handout. We looked at the first part. Feel free to use that video for that first half. And now we're going to take a look at the second half, right? So as we're looking at it, we're going to use this expression that we learned about prior, and we're going to figure out how we can apply it. So this expression is called Coulomb's Law. Notice you have definitions on the right. This is coming from your chemistry reference table. And so let's go ahead and break this down into its parts so we can just confirm our information and feel a little bit confident about it. So F right here is our force, right? It's how strong or weak our attraction or repulsion is. So how much do two objects want to either repel each other or attract each other? So imagine that you have one object and you have a second object, right? I'm gonna call this one object 1. I'm gonna call this one object 2, right? And so object 1, let's say, has the charge of Q, and because we want to label things easily, notice Q says charge here. I'm gonna call this charge for object 1. And then this one, it also has a charge, and it's going to be the charge for object 2. So it has a little 2 on it, right? And then I can think about how far apart they are from each other. And so that is its distance, right there, right? And so I could change the charges on any of it, or I could change how far apart they are. I could bring them closer together. I could bring them farther apart, right? All the things I can change. So this expression, Coulomb's law, is just saying that if I increase the distance, or the distance squared, notice it's squared, right? Then my force, or my attraction or repulsion, is going to go down because, y'all, it's on the bottom, right? And if it's on the bottom, that means it's being divided. So a bigger number dividing is going to make a smaller force. You can also think about it in terms of magnets, right? Think about a fridge magnet. If I'm really close to the fridge, so my distance is really small, then my attraction between the magnet and the fridge is going to be pretty strong. It's going to want to stick, right? But if I take that magnet and I go all the way down the street, right? I walk out the door, go down the block, maybe another block. My distance is really big. It's going to be a really big number, but it's definitely not going to go and attract to the fridge, right? Because the force is going to be so small. So as I increase that distance, my force of attraction or repulsion is going to get smaller and smaller and smaller and smaller, right? And so that is this inverse relationship that we have going on. And so we can actually figure out how much bigger or how much smaller a force is by using this expression. Right? So that's the way we're going to apply it. So let's go ahead and keep taking a look down below. Let's use this example. So if we look at this first example, you're going to come back and use these metric prefixes later on. So if we look at this example, right, what we have going on is that you take a balloon and you rub it on a sweater and a bunch of electrons transfer over, right? So imagine, right, let's draw our sweater. I have a short sleeve sweater, that's okay. And we also have a balloon. And after we rubbed the balloon on the sweater, it says that 1.2 times 10 to the 10th electrons moved over. They moved from the sweater to the balloon. Now, remember back when we talked about electrons. Electrons, sometimes we put a little minus sign on them to remind ourselves, have a negative charge. Right? And so if we started off neutral and then we rubbed them together, right, suddenly there's going to be some kind of charge thing going on because we moved over things that are negative. So if I moved over this many electrons from my sweater, that means my sweater is now missing that many electrons. And that means my balloon now has that many extra electrons. So if there's extra electrons, that means it's going to be extra negative. So suddenly my balloon, super negative, right? And that means that my sweater lost all of those negatives, so it's going to be positive. So that's the first thing we want to think about. The next thing we want to think about is, what is the charge going to be, right? But each of these electrons is one negative charge. Each little dude has a charge. And so if we think about it, right, let's do a little comparative. If instead of moving over that many electrons, we moved over like 5 electrons, let's say. It was just like a really quick situation, right? If we just moved over 5 electrons, that means that the balloon, we'll make this Q2 because it's on the second side. That means that this one would have 5 extra negatives. So that means its charge would be -5. And the sweater would have lost 5 negatives or lost 5 electrons. So that means it would have 5 positives. And so we'd have this scenario going on. But y'all, we don't have this going on. We have not 5 electrons, we have 1.2 times 10 to the 10th electrons, right? That's a lot more. So we're gonna kind of escalate our scenario. I thought this was gonna be a bigger eraser. Sorry. Okay. So instead of moving over 5 electrons, we are going to move over 1.2 times 10 to the 10th electrons, which means that the balloon has now gained 1.2 times 10 to the 10th negative charges or negative electrons. So that means its charge suddenly is now 1.2 times 10 to the negative 10. But negative, right? Because it gained electrons. And over here, this sweater lost 1.2 times 10 to the 10th electrons, which means that now it's missing those electrons, so it's become that much positive. And so now we have this positive charge going on. Okay, so that's the first thing we want to think about. That's just the first sentence, y'all. So the thing that this question's asking though, right, now that we've actually gotten to here, it's a 2-part question. One, it's asking about how does the force change when the distance changes from 10 to 1, that's important, and is it attractive or repulsive? So if we recall, identifying if it's attractive or repulsive, we got this, right? That line got real big, so I'm gonna fix it. So think about your charges right now. If your charges are the same, right, then we would have repulsive. If they are opposite, we're going to have attractive. So take a look at Q1, take a look at Q2. Are they the same or are they opposite? And that is going to tell you whether you have repulsive or attractive forces. I'm going to let you think about this one, okay? And so now, let's take a look at this force situation. So if you recall from above, in our formula, the charges are on top, and then there's d squared underneath, right? So let's go ahead and take a look at what is going on here. So maybe we can resolve how the force changes. This is just like the lab we did. All right, so I'm gonna make 2 scenarios because I find that to be a little easier. I'm gonna make a scenario A and a scenario B. Whoops. Imagine that's a B. In scenario A, I have Q1 and I have Q2. And my distance says it's 10 centimeters right there, right? But remember, I gotta square it. So that means it's gonna be 10 centimeters, and I'm gonna square the whole thing. Okay, in the second one, notice that the charge isn't changing, right? The question isn't saying that the charges got bigger or smaller, right? So that means I'm still using Q1 and Q2. And below though, my distance did change. My distance changed to 1 centimeter, and then I'm gonna square it. All right, so let's go ahead and do some simple calculations. If we take a look at our 10 centimeters squared, we gotta square everything. So that means that this becomes 10 times 10, right, to be squared. So let's go ahead, we're gonna rewrite this, Q1, Q2, over 10 squared is 100, and centimeter squared is just centimeter squared. And then over here, we still have Q1, Q2, and then underneath, 1 squared is 1, and then centimeter squared is centimeter squared. So notice that the difference between these is only on the bottom, is only on the denominator. Q1 and Q2 are the same, but underneath you have a whole thing going on. So this force has 100 here, and this one has 1. So to get from 1, oops, I'm gonna go the other way. To get from 100 to 1, right? This is this is 100 times smaller, right? Which seems really confusing, but we're dividing by a much smaller number, which means that this force, our original force, is 100 times smaller than our new force. So F1, or FA, we'll call it A because it was scenario A, is 100 times smaller than our force in scenario B. You can also say that the force in scenario B, is 100 times bigger. So you could also write it that way, right? Either way, and that is how you're going to be thinking about it. So that is also how you are solving part B. We're just putting it in this blank space because we're talking about it, right? So this is how you would explain visually and through mathematics how you know that your force is 100 times bigger in scenario B. So that's the way you want to think about it. As you're kind of working your way down, and then you can decide if it's attractive or repulsive, and then you can describe in words how the force changed, right? Every question further down, I'm sorry about the numbering, is using that same strategy. Make 2 scenarios, compare them, and then decide what is happening to your force. So you're going to do the same thing going forward.